As mentioned in our previous introductory video, we want to focus on three questions. The first is what makes a mapping one-to-one, then what makes a mapping conformal, and what does Laplace's equation map into. So we'll address those in the next three videos. But in this video I want to talk about elementary mapping functions in particular, because I want to just give us a good intuitive feel, geometric feel for what these mappings are doing. So these elementary mapping functions, they're again very simple, that's why they're called elementary, and by themselves they aren't terribly useful necessarily, but we can put them together to get more complicated and more useful mappings. So let's start with simple translation. So if my mapping function, my w is f of z, is simply z plus a, where a is a complex constant, then that's going to translate in the complex plane or point z to the point w. So it'll look like this. So if I have my complex plane, x and y, and then I have a point z somewhere in my z plane, so we'll label that as z. Now the constant a, which is complex, is going to translate this to a new location w in the u v plane. So I'm superimposing the z plane and the w plane in all of these that I'm going to show in this video just to keep things relatively straightforward. So we're simply translating along the x-axis according to the real part of a, and then along the y-axis according to the imaginary part of a. So that's just simple translation. So now let's take a look at stretching. So our w as f of z is simply b times z. B here is a real constant. As always, we can choose to represent our complex variable z in Cartesian coordinates, x plus I, y, or polar coordinates r e to the I theta, whichever is the most convenient. Here we're going to use r e to the I theta. So z is r e to the I theta. So then the modulus of w is simply b times r. That's this piece out front. And the argument of w, which is the angle in the exponential, is the same as the argument of z, which is simply theta. So the way that looks on the complex plane is as follows. So again, our x, y axes, and now I have a point z here, say, and that's r from the origin and angle theta from the positive real axis. So again, using polar coordinates in this case. Now, the argument stays the same for w, so it's just moved further out according to b times r. If b is less than 1, then it's closer to the origin. If b is greater than 1, then it's farther away from the origin. But as you can see, it's just a simple stretching. It moves our point z out on this radial line from the origin to the point w. That's stretching from the z plane to the w plane, uv. All right, let's look at rotation then. So our w as f of z is now e to the I alpha times z. Alpha here is real, and it's the angle through which we want to do the rotation. Positive alpha is a counterclockwise rotation, just like theta, going from positive real axis counterclockwise. So by multiplying z times e to the I alpha, again, we're going to use the polar form. Z is r e to the I theta. So the modulus of w will still be r, so the radial distance stays the same. But now we have e to the I alpha times e to the I theta, which is equal to e to the I times the quantity theta plus alpha. So that's a addition from the original argument of alpha. So graphically, that looks like this. So again, x, y for the z plane. And we have our point, say, z here, which is r theta, just like before. But then it's now going to rotate through an additional angle alpha. It'll be the same radial distance away, r, and that's our point w in the uv plane. All right, so again, z to w, same radial distance from the origin. We simply add theta plus alpha. Alpha is now the argument of w. Now we could combine the stretching and rotation by having our constant times z, where the constant is a complex number. If c were complex, then the b in the stretching would be the modulus of c, and in the rotation, the alpha would be the argument of c. So we can combine those two together in that way. Now here's another one that's sometimes useful. W is f of z is 1 over z. We call that the inversion mapping because we're inverting z. It's the reciprocal of z. Once again, we could use x plus iy or re to the I theta. We're going to use the polar form once again here. So I'm going to have z is re to the I theta, and w is rho e to the I capital theta. So w is rho e to the I capital theta. 1 over z is 1 over r times e to the minus I theta. So therefore the rho and the 1 over r have to be the same, and the capital theta and minus theta have to be the same. So all the points inside the unit circle, which is a circle centered at the origin of radius 1, in the z-plane are then mapped to the region outside the unit circle in the w-plane. That's what the rho is 1 over r does. And then it gets reflected about the real axis because that's what the kappa theta being minus theta does. Let's look at a simple example of that. So here's z is equal to 1/2 I. So w is 1 over z, so that's 2 over I, just the reciprocal. And 2 over I, multiply top and bottom by I, you get minus 2i. So here is the point 1/2 I on the x, y plane, or the z plane. And the mapping, f of z, then maps that point to minus 2i, which is down here. So it took a point inside the unit circle and moved it out because of the 1 over r. And then it also reflected it about the x-axis, the u-axis. And that's what the inversion mapping does. Now, the inversion mapping will always transform circles into circles or lines. A line is simply a circle with infinite radius in the context of these mappings. So we could take that unit circle and map it into another circle, or we could map it into a line if we desire to. Now here is one that truly is useful in its own right, the linear fractional transformation, or sometimes called the bilinear or Mobius transformation. So here the mapping w is f of z is az plus b over cz plus d. The a, b, c, d constants are all complex. All 4 of them can be complex. By choosing different values, specifying different values of those 4 constants, we can get a whole variety of different mappings that are quite useful. There's more information in Appendix A if you're interested in some of the derivations behind some of the things that I'm going to say and results that I'll show. There is only one requirement on these constants, and that is that a times d is not equal to b times c, and that is addressed in Appendix A. One of the nice things about this mapping is when you write it in its inverse form, so you write z is capital F of w, you also get a fractional transformation. So it has the same properties both directions, from z to w and w to z. One of the ways that we can use this is to specify 3 points in the z-plane and 3 corresponding image points in the w-plane, and then use this implicit relationship between them to get the fractional transformation. Here is the result. Once again, if you want a derivation of this, you can see it in Appendix A. But here are the 3 points, the w points on the left, w1, 2, and 3, and the corresponding image z1, 2, and 3 points on the right. And by specifying those in particular ways, we can get interesting and useful fractional transformations. So let me make a number of remarks about this. So it's proven in Appendix A, this important result of fractional transformations, that lines and circles are mapped into lines and circles. So I can map lines into circles, circles into circles, circles into lines, and so forth. And that gives us a nice geometric representation or interpretation of what this fractional transformation is doing. Now remember, lines are simply circles with infinite radius. And sometimes it's actually useful to put points at infinity. So our triplet of point z and the triplet of image points w, any one of those could be put at infinity if that produces a useful transformation. So the way that works in equation 2.1 is, let's say that w1 is equal to infinity. So where does that show up here? Well, here's a w1 and here's a w1. So you notice that every w and every z appears in the numerator and the denominator. There's a factor in the numerator with that value and there's a factor in the denominator. And you can prove, and this is done in Appendix A, that that ratio of factors, in this case W minus W1 and W3 minus W1, you can simply replace it with 1. And so if W1 were 3, then you would end up with just W3 minus W2 over W minus W2 on the left-hand side. Okay, so that will prove useful. Now these other elementary mappings that we've looked at, those are also special cases of the fractional transformation, so they carry over these same properties. Again, just refer to Appendix A if you want more details on these fractional transformations. As I said at the outset of this video, the real power of these elementary mappings is that we can combine them together. So we can do a stretching, we can do a translation, we can do a rotation, we can do inversion. We can combine these together to get more useful mappings in practice. There are a number of books, or you can look online. There's software available as well online, where you can play around with these mappings or look through the tables of various mappings and what they map in the z-plane to the w-plane, and that can help generate some ideas of how to go about doing these mappings. So once again, in principle, any complex function could be regarded as a mapping. However, we have certain properties, such as it being one-to-one or conformal, that are desirable in these mappings, and we'll talk about those in the subsequent videos.